Hello, engineering materials. This is a solution to one of the exam problems. We have an iron carbon system, so over on this side would be 100% iron. Over here is, well, it's not 100% carbon, it's this other phase called cementite. Uh, which we learned if you don't take a very long time to cool it, the cementite phase will form. The cementite is the Fe3C phase. Okay, and that's around 6.69% carbon. Okay, so what we started with was a sample that was 1.5% carbon, and at some temperature that put it like in between 1,000 and 1,200, so it was definitely 100% austenite, and you were asked to draw a microscope picture of this, which would look like, and I think a lot of you got this right, it's going to be individual grains, and that stuff is going to be austenite, and that austenite is 1.5% carbon. So it's a 1.5% carbon austenite. Okay, then we cooled it a little bit further, down to point B. Now, I didn't ask you to do this on a test, but I think looking at some of your answers, I think some of you would benefit to see what happens when we cool it to point E first. So point E is just this point right here. So just as we pass this phase boundary between 100% austenite and then a mixture of two phases, let's see what that looks like. So at point E, it's going to look an awful lot like point A. We still have these grain boundaries from point A of austenite, but as I move to point E is going to be a mix of austenite, that blue dot, and cementite over here. So E is a mixture of both these two phases. And is it going to be mostly austenite or mostly cementite? Just, say it out loud. Yeah, mostly austenite, because point E is really close to the austenite side of that. You could, of course, do a calculation, and what you'd find is that E would be like 99% austenite. So it's mostly austenite with just a little bit of cementite. And austenite was a solid. So as I transitioned from A to E, somehow the cementite formed. It's going to form at the grain boundaries because the diffusion rate is a little bit higher there. So the cementite is going to form, and I'm going to draw that on my diagram here. I'm going to draw just a little bit of, so I'm going to, at the grain boundary, I'm going to make that a little bit wider. So it's mostly still austenite, but there's little bits at the grain boundary of cementite forming. So the diagram would look like that. And of course, the cementite at this point would be 6.69% carbon, and the austenite would be a little less than 1.5%, maybe 1.49% carbon, something like that. Okay, and as we cool from E to B, which is what you were actually asked about on the test, as we cool from point E down to point B, what happens is the ratio of the austenite to the cementite changes. And at point B, ask yourself, am I going to have more cementite compared to point E or less? Answer, more. So, and if you do a calculation, which you were asked to do here, we can figure out exactly how much of each. Okay, so let's flash to that calculation. For that calculation, we know that the total sample has to have, this is the carbon in the sample has to equal the carbon in the sample. Okay, so the total amount of carbon in the sample has to equal the amount of carbon that's in the austenite phase plus the amount of carbon that's in the cementite phase. the amount of carbon in the sample, since it's 1.5% carbon, of course has to be 1.5% times the total mass. The amount of carbon in the austenite phase has got to be the fraction that's austenite times the total mass times the percentage of that that's carbon. And of course what's left, that remaining fraction, has to be cementite. The masses cancel from both sides, indicating the total amount of mass of your sample isn't going to matter. And we get this equation, which we solve for F, which gives us 87%. Now we have to ask ourselves, that's 87% what? 87% austenite or 87% cementite? Well, it depends on how you set up your equation. Here, that F was referring to this term, which was our austenite term. So that's 87% austenite, which means it's 13% cementite. And that cementite itself is 6.69% carbon, and then the remainder, which is 93.31% iron, and the gamma phase there is the austenite, and that is at this temperature for point B. Point B was picked because it's just barely above that eutectoid temperature. So that's why we were able to read that number off the graph so accurately. It's 0.77% carbon, and then the remainder, which is 99.27% iron. Okay, so an answer to that question of what are the exact compositions at point B would be this box here. 87% austenite and 13% cementite. Okay, back to our diagrams. We moved from E to B, and we now have 13% cementite. So I've got more cementite. Where is that cementite going to be formed? Answer, it's going to be formed at the grain boundaries. So point B on the graph is going to look like point E, except there's more of it at the grain boundaries. So it looks, grain boundaries are a little bit thicker with cementite. So this is the austenite, oops, and this stuff here is the cementite. Okay, and as we go from B to C, I've now gone below this temperature, this 727 degrees Celsius. And when I go below that temperature, the austenite that we used to have now can no longer exist. Can't exist below 727 degrees. So when I go below the 727 degrees, this picture is going to look the same, except the austenite that we had here. First, let me draw it. So this is the same picture, or an attempt to draw the same picture. Okay, except now the austenite no longer exists. And when I dipped below that temperature, the austenite had to separate into the alpha phase and the cementite phase. It all happened at once. So it didn't have time to make nice big crystals of cementite and nice big crystals of ferrite. So it made actually very fine layers of cementite and alpha, which is called ferrite. So what it looks like is, or of course this is a quick diagram. I'm drawing this stuff on the diagram with these lines just to indicate very fine layers of ferrite and cementite. And this stuff has a name. This stuff is called pearlite. Okay, so that's perlite. This is cementite. Okay, and finally I asked you what would happen if, instead of lowering the temperature further, I asked you on the test to draw a diagram for what I'd have if I cooled a sample down to point D. So what if I had cooled it and it started at 0.7% carbon instead of starting at 1.5% carbon? Well, if I'd started at 0.77% carbon and I cooled it down to point D, then we never would have had any cementite split off at the grain boundaries. So the percentage was 0.77%. So it would have stayed 100% austenite all the way until I got to the eutectoid temperature. And if I cooled below that, all the austenite would have frozen at once. So the diagram here would look like, there's my grain boundaries. If by coincidence I got the same grain boundaries. But all the austenite would freeze. There'd be no cementite at the grain boundaries. So it would look like something like that, where this stuff here is called what? What is this stuff? Yep, you're right. It's called perlite.